quick question. So for this, it's just as long as you show that for like a certain pair MN, there exists an arrangement of MN beads such that it satisfies, then that pair MN is okay.
Yes, what's your problem exactly?
So, oh wait, no, I just wanted to clarify. So it just as long for any pair MN, you need to show one that for one like coloring of the MN beads, it satisfies the condition.
Yes. For any colorings? No, for any colorings, obviously, we cannot say it's good. You should prove, I think, there exists a good coloring. Because
Okay.
let's check for a small example to understand it is exactly what. Uh, let's consider, for example, M2 and 2. Okay. If you consider M2 and 2, then how many beats are there?
4.
Yes. So how should we color this from this one?
3 red. Oh no, 3 blue, 1 red.
Also 3 reds, 1 blue, or
Okay.
this one works. Because look, it says it turned out that no matter how the necklace was cut into M blocks, 2 blocks of 2 consecutive beats. Okay. So in how many ways we can cut this into 2 blocks of 2 beats?
2 ways.
Exactly. You can say like this one or like this one, right? So in this case we have 2 1, and then here again we have 2 1, and they are different, right?
Right.
So we should prove there exists a good coloring, right?
Okay.
Because we agree all colorings cannot be good, because if all of them equal
Blue.
reds, then it's not possible, right? For any M and N.
Right.
So we should find all M and N that there exists a good coloring, right?
Alright.
Want hint or wanna keep trying?
I'll keep trying.
Okay, sure.
Can you give hint?
Small example. One more hint or that's enough?
Because I've tried with small example, but like because I'm trying MS3 right now.
Have you checked M2?
Yeah, MS 1 and 2 is good for all N.
Exactly. What about M3?
M3 is good for N is 2, but I'm trying for N greater than or equal to 3, and I'm not sure how to either show case where it's okay or how to prove that it's not for all cases.
Okay, for M3, what should we prove?
That the 3 blocks of N beads has different number of red.
Yes, why N cannot be 1?
Oh, N. Oh, sorry. N plus 1 has to be greater than or equal to M, or N is greater than or equal M minus 1. Because
Why?
you need 0 to N. Oh, yeah.
Exactly. 0 to N minus 1, right? You have at most this. It should be at least M. So N should be at least M, right? N plus 1, 0 to N should be at least M. So M plus 1 is at least M, right?
At least M. Yeah. So at least 2.
And at least 2. Have you checked M3 and 3?
I've checked, but I can't. I'm not sure how to disprove, or at least because I couldn't find a good case.
You have a good case. Let's check it together.
Oh.
Want me to tell you the example is what? Let's check this example to see it works or not. So, suppose our Let's see this example is good or not. We want to divide it to so let me change it to this. We want to see this example is good or not, right?
Mhm.
Do you agree if we cut like this, then it's good?
Okay.
210. If we
Okay.
cut like this, then again 210, right? If we cut like
Okay.
this, it is like first one, right?
Right. Okay.
So it is M3 and 3.
Huh?
Now
Oh wait,
check
isn't that
what?
N3 N2?
Yes, sorry. Here, M3 and 2. Then next step, we should consider M3 and 3, M3 and 4, and try to generalize for M3 and any general N. Okay. Then
Oh wait,
try.
is M3 N3? That's possible though. Is it?
Let me check. I think so. Let me. For M3 and 3, we can say this. 3, 1, 2. But if you consider like this, 2, 4, 5, 3, 4. If you consider like this one is good,
Oh, I
first
didn't.
one, right?
Yeah,
First one
but
is good,
then
but second one would be bad, right?
oh yeah.
Because 1, 1. Because of this, try to make this one odd. Now, we should check 3 cases, right? Here.
Right.
So, the first one, second one, and third one.
Okay.
So then it would be 3, 2, 1. This one again 3, 2, 1. This one again 3, 1, 2. So this example is good, right?
Okay.
So M3, M3. I think we should prove that for. You said what is greater than equal what?
N+1 is greater than equal M.
N plus 1, yes. Greater than, because in each of them we have n bits. So we can have 0 to n. M plus 1 should be at least m because we have m blocks. Let's check n plus 1. Yes, because for example, if n is 1 for m3, then we can have 0 red or 1 red, right? And it's not possible to have m different cases, right? Okay, I think if we consider this condition, then we can find always a good example. For all of them, I think it's good. So, 90% I think it's correct. And because it's the problem of USAMO 2024, okay? But by a small example, we want to solve this. So, try to check M3, 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 N4, M3 general N, and then try to generalize it for general M. One hint or want to keep trying?
I'll keep trying.
Okay, sure.
Oh wait, can you give hint? Because I only got until MS3. I'm not sure how to generalize after.
Can you explain M3?
Oh, I divide into N is even and N is odd, but um for N is even, it's basically um N+1 consecutive blues and then 2N-1 consecutive reds. And then for odd, it's similar, but then you have an additional red in between the um last two blues.
Mm-hmm. So if we generalize this coloring is what? First, we can split the beads into 3 parts, right? Like this.
Mm-hmm.
1, 2, 3. And for first block, first 3 beads are red. For second block, first 2 beads are red. For third block, first one is red, right? So let's see, can we generalize it? 1, 2, 3 to n, right?
Right.
Minus 2, n minus 1, n. Then consider, again we can say we have 1, 2 to n, right?
Mm-hmm.
3, n minus 2, n minus 1, n. Then we can say, okay, 1, 2, 3 to n, n minus 1, n minus 2, right?
Right.
So in first part, we have this, right?
Mm-hmm.
And the colors. Because the colors are all of them, then n minus 1, then n minus 2. It is exactly like this one, right?
Right.
3, 2, 1, right?
Mm-hmm.
We want to see, does it work for all n's or not, okay?
Okay.
So let's see, here in this case it's n minus 1, n minus 2, right?
Mm-hmm.
What about next one? Next one would be this, right?
Right.
Then it would be what? n
Then.
minus 1. The next one has to be n minus 2, right? Because some of them should be equal, right?
Right.
Agreed, because consecutive ends,
Yeah.
here all of them are red except this one, right?
Okay. Okay.
Okay, now do you agree if we continue, next one again would be n minus 1, n minus 2.
Mm-hmm.
If we consider this one again, we have n because all of them are red, right?
Right.
Okay. And until which one is n? For example, let's try to do something. Let's consider for this one, let's use I, okay? To
Mm-hmm.
make sure it's good or not. So here, if we consider I, so let's erase or let's move this here. Let's move it like this. Let's move it this one, this one. Let's move this one. Okay, so suppose it is I, okay?
Mm-hmm.
And this one is I. This one is I. But when you want to connect after I, here we have n minus I. Suppose it is I plus. Here we have n minus I, right? N minus I
Right.
plus I. So we should connect this one to this part, right?
Mm-hmm.
Agree.
Right.
And then here again we have n minus I. You should connect this part to
Mm-hmm.
this one, right?
Connect to. Okay.
It's
Yeah.
like n minus I. It is our case, right?
Mm-hmm.
Now let's see how many reds are there. So we can guess that this part always have n
And
reds,
red.
right? So let's check. For 1 it's correct, for 2 it's correct, for n minus 1 also it's correct, but for n it's... For n this part is... this.
Okay.
So we can consider I can be from 1, or do you agree I can be... So, let's consider this one A, okay? This vertex A. A, do you agree we can start here as A, at this point, this part to this part, right? This part, do you agree, is exactly similar to this one?
Okay.
If we cut
Yeah.
from here, it means that we cut from here, right?
Right.
So we can say that A is here always. So if you consider like this, A, B, C. For AB, AB always has how many reds? By this definition.
AB has
This edge.
N.
Exactly. Always has n reds, right?
Yeah.
BC has how many reds? And I can be what? I after I can be n here 1 to n minus 1, right?
Okay.
BC. For BC, let's see what are the cases of B. If we start here 1, then it would be this. So B can be here, right?
So N minus 1.
B can be here, yes. 2B can be only at the end of n minus 1, right? So BC has, and the red can be, this one can be from what? If it is here after before 1, before 1, before 1. C, do you agree, can be here, can be here, can be here to this part. Before 1 to before n. Agreed? C can be here to here. Okay, so
Right.
BC has how many reds?
N minus 1, or wouldn't it be N minus 1 or N minus 2?
Let's check. Look, if it is when it is after n, this one and this one, do you agree this one corresponds to this one? Here it is n minus 1, right? If it is like this, again n minus 1, right? And if it is similar to this one, n minus 1, if it is like this one, n minus 2, right? So all of them are that except one, n minus 2.
Right.
And okay, so CA would be what then in this case?
If it's N minus 1, then N minus 2.
Yes, because some of them is n plus n minus 1, n minus 2. This one is what?
N minus 1.
Yes. Now I want to generalize this. Can you guess that? How can we generalize it? For general, we proved for M3 and n, right?
Right.
Okay. If it is m, want me to tell you how we should generalize for m and n, or want to find it on your own? Coloring. Want me to tell you coloring should be okay. Is it what?
Oh, is it
How many
one
blocks are there?
side?
We have m blocks, right?
Right.
In each of them we have how many beats?
N.
Exact. So for first one, how many reds are there?
Is it N reds?
Exactly. All of them reds. Next one.
Is it all red except for last one?
Yes, first n minus 1. And last one should be what? Or let's write for I. If we consider for ith block, how many reds are there?
Is it N minus 1 red and 1 blue until the mth where it becomes
No,
2 blue?
Let's
Or is
consider
it
this.
different?
First block, number of reds. So it's non-block. How many reds are there? First block, n. Second block, n minus 1. Third block, n minus 2. 2 ith block would be what?
Oh.
If you want to.
It would be
Yes,
n minus 1, n minus I plus 1?
exactly. So you should have first n minus I plus 1 should be red, right? And then the rest blue. Which is what? Which is I minus 1, right?
Mhm.
And what about for mth one? How many reds are there?
N minus m plus 1.
Yes, n minus m plus 1. How many blues are there?
M minus 1.
So number of blues would be 0, 1, 2 to m minus, right?
Mm-hmm.
And we know that n is at least, n plus 1 is at least m, right?
Right.
Or n it's at least m minus 1, right? So m minus 1 blues
Mm-hmm.
always would be less than or equal n, right?
Right.
Okay, so now you should consider again different cases. If we start from here to start from here, right? And prove that in each case we have m different uh, number of reds, right?
Oh, okay.
For proving this part, one hint or want to try on your own?
I can try.
Okay, sure. Try. One hint or wanna keep trying?
Can you give him?
Okay, sure. So let's try to count each part together, okay?
Okay.
Take on the first case, then number of reds would be what?
Oh. Oh, sorry. Like first position.
Yes, for example,
It's
if we start from here, right?
oh, and then so it's n minus 1, n minus 2 until n minus m plus 1.
Exactly. So let's check all cases. So, how many cases should we consider? We should consider how many cases? For example, first case, this one. Then from here, here. In each of them, we have n
N cases.
n cases,
Oh
right?
no.
If we start before this,
Oh,
if we start what?
oh, sorry. No, never mind.
We have n reds. Start if you start from before first one, before second one, before third one, before nth one. This one will be same as this one, right?
Mm-hmm.
So if we start here, suppose we call it 1. Let me. Okay, yes, that's good. If we start before second one, second case, third case, to nth case, right? So for each of them, we want to see number of reds in first box, in second box, in third box, to m box, right? Mth box. Now, if we start from this point, from point 1, then as you said, we have n reds, n minus 1, n minus 2 to n minus m plus 1, right?
Mm-hmm.
If we consider second case, then it would be what? Before second case.
Second case. N reds for the first box, and then
Yes, for each of them, do you agree? We consider this on to first one, right? Then here to first one of next one, right? And we
right.
know that what is greater than equal what?
N is greater than m minus 1.
So n minus m plus 1 is at least 0, right? So this one maybe 0, maybe at least 1. So in first one, how many reds are there?
N.
Yes.
then
Here n.
n minus
Next one.
1. N minus 1.
Yes, n minus 1. Then, for example, for third one, would be what?
N minus 2.
Yes, look, as you can see, we shift 1 unit, right?
Right.
Do you agree always, except this one, because we don't know it has red. Always we remove 1 red, right?
Oh, and then add 1 red.
Then we add 1 red, but we should consider for which case we won't remove 1 red. So, if n minus m plus 1 is at least 1, do you agree each of them has at least 1 red? First one of each of them is red. So do you agree always you remove 1 red and you add 1 red? Because first one, when n minus m at least 1, n minus m plus 1 is at least 1, then you can say, okay, in each of them we have at least 1 red in each box, right?
Right.
So you remove first red of one box, first bit of one box, and you add first bit of next box, right? Because first one is red, it has no effect, right?
Right.
So it would be n minus 2 to n minus m plus 1, right? Now for this case, we should consider n minus m plus 1 is equal to what?
Is equal to 0.
0. If it is 0, then what can we say?
Then the last part will be
Only last part doesn't have red, right? All of them would be blue. For these boxes, again, we have same thing, right? n minus 1, n minus 2. Now, instead of this box, let's write something. If we consider previous to this one, or m minus 1, and here m minus. For m minus 1, we have only 1 red, right? In this case. So, we remove 1 red and we can't add any red, right?
Oh, right.
So then it would be what?
0.
n
Or no,
minus
n minus m
m minus m was what
plus. Oh,
in
sorry.
this case? Before that, we had n minus 1, n minus 2.
N minus m plus 1.
It was 1, it was 0 before switching, right? In this case. So, it would be n minus 1, n minus 2. 1 would be what?
0?
Yes, and next one would be what?
1.
Yes, only we should switch 0 and 1, right? And for both of them, previous one is 2, 2, right?
Right.
So we proved always the second one would be good, right? We can check third one and so on, or we can jump into I, okay?
Okay.
So let's see what happens if you consider from ith one, okay? Or because here we have I, let's consider jth, okay? So we can say what? We can say, let me move the things. Let me move it. Okay. So if we consider jth one, I want to consider the case that before jth red, okay?
Okay.
So before jth red, then if we consider second box, what happens? It goes before again jth one here, right?
Right.
Again we go okay. Before jth one here. So if we consider this box, or let's consider like this. If we consider before jth red, before jth red. Like this, right? So how many bits do we have here? How many bits do we have here? Not how many reds.
Oh, It's
Not how many reds, how many bits are
n
there?
minus j and j.
Yes, n minus j bits and j bits, right? J can be from what to what in general, at
J
least.
can be 1 to n?
Exactly.
No. Oh, wait.
Yes, 1 to n. Because before first thread to before nth thread, right?
Oh, okay.
Okay, and now we want to consider, okay, and let's consider we call this first one as first box, okay?
Mm-hmm.
This one as first box, and second one and third one, okay? So,
Okay.
we want to consider number of reds or number of blues. Do you agree if we prove number of blues in each of them? If you consider number of blues in these boxes, if number of blues be different, do you agree that number of reds also should be different?
Right.
Okay. So let's calculate this box. For first box, for first part like this, for second part like this, for third part like this, to mth parts. We want to see are they different or not, okay?
Mm-hmm.
For first box, how many reds are there?
Um, this is for all j or for
Yes, for all j's. Can we say, or it
if
depends on j?
oh it's n reds.
Yes, always n, because j is at most n, and if j is n, we should consider before n. We should consider this one, right?
Right.
So first box always has n reds and 0 blues, right?
Right.
What about second case? Second box.
If it's n. Oh, it's either n minus 1 or n minus 2. If it's n minus 2 if j is n.
So let's consider. It's before jth one, right?
Mm-hmm.
It's first one, jth one. So we should consider like this, right?
Mm-hmm.
We don't know how many reds are there. Here we know how many reds. Do you agree we can split each part to first part and second part of that? For example, here, n minus j and j, right?
Yeah.
So let's consider number of reds. Let's number of reds of first part, number of reds of second part, and sum of them, okay?
Mm-hmm.
So for first one, do you agree it's what? This part, how many reds are there?
And oh no, n minus j.
Exact, good job. N minus j, let's check. Look, it says it is before jth one, so it is jth one to nth one. J to n is what?
Oh, n minus j plus 1?
Exact. And this one would be what? R2 second box,
J minus 1.
which is n, right?
Mm-hmm.
Now for box 2. Here, how many reds are there?
N minus j. Yeah, n minus j.
Do you agree we should consider decreasing order for these? For 3, it
Right.
would be what?
For 3 would be.
Because we are considering second part of each box, right? Second part
N
of
minus.
these, first box of this one. So here in each step we add one more b, right? So in next part, do you agree we should decrease it by 1?
Right.
N minus what?
N minus j minus 1.
Yes. And we should consider until which part it in which part it would be 0.
Right. Oh, it'll be 0. And
It is first one, second one, n minus j third one, n minus j minus 1 fourth one, n minus j minus 2. In which part it would be 0?
N minus j plus 2?
N minus j. Good job, yes. Because some of them are equal. Or you can work on this as an arithmetic sequence, right?
Alright.
Okay. Good job. Now, after this, what happens?
After this,
For example, in n minus, because we can't have negative, right? So, let's see in n minus j plus 3, then how many reds are there?
n minus j plus 3. If it's uploaded. Isn't it? Oh, wait. Isn't it still 0?
Yes, it's still 0 until which box?
Until m?
Until m. Exactly. So for m minus 1 also it is 0, right?
Right.
And for m it would be what?
It's also 0.
Yes. Good job. So until n minus j plus 2, we have this. After that it would be 0, right?
Alright.
And at the end we should check some of them to make sure, because some of the reds should be what? 1, 2 to n. No. N to n minus 1 to what?
To n minus m plus 1.
Yes, at the end we should check that
Oh, wait.
some of all reds.
Do we need cases for j?
We can check at the end, but let's check something good, then at the end we would check special cases. Okay?
Okay.
Okay, now second part. R2 here. Then here, right? Second part would be what? For first box, it's what? J minus 1, you said, right?
Right.
What about second, this one? The second part, how many reds are there?
J minus. Oh, wait. Because it's minus j 1.
Yulia wakes up and gets scared when she sees Maruko next to her. He tried to kill him. Maruko tries to clear it and says, "Just let it go this time. It's better to pretend."
In this case, let me tell you.
It's still j minus 1.
Exactly. Because j minus 1, because we have lots of R's, right? And
Right.
so until which box it would be j minus 1?
Until. Oh, is it n minus j plus 1 box?
Yes, because in n minus j plus 1, some of them is what? In first box we have n, right? In first box we have n, in second box n minus 1. Some of them is n plus 1, right? Agreed. So here, how many R's are there in this box?
J.
But do you agree next box also would be good, because we need j minus 1, right? N minus j plus 2. How many reds are there here?
J minus 1.
Yes, agree. For also this box it's good. For next box then we have less than that, right? For next box n minus j plus 3. How many reds are there?
J minus 2.
Yes, and because if we consider this one, we are considering first j minus 1 beats. So, do you agree until n minus j plus 2 it is j minus 1? After that it is smaller than that. Agreed?
Agree.
So for n minus j plus 2, it would be j minus 1, all of them, right? For this one, it would be
Right.
what?
J minus 2.
Exactly. Until what?
Until
This monster from yesterday was the worst you
um
saw. On the other side, Anna wakes up lazily.
It will be decreasing, right?
right.
Eats breakfast and shares virtually Naruto.
So in which part it would be 0?
The light flicks.
And would it be 0? Maybe it's not 0, right?
Right.
We are considering first j minus 1 cells of each of them, right? Maybe it reaches 0, maybe it won't reach 0. Exactly the case that we considered here. Maybe it reaches 0, maybe it won't reach 0, right? It reaches 0
Right.
earlier, or it reaches 0 at the end, right? Okay, it reaches 0. Okay, so let's consider this. So here, under what case we reach 0 before m?
Because if you don't reach 0, wouldn't it be like m minus n plus 2j minus 6?
Some of them is what? From here it is decreasing. Because here also it is increasing, some of them is constant, right? So n
Right.
plus 1, n plus 1, right? Some of this one and this one, the agree is always n plus 1.
Yes.
Okay, so if it reaches 0, then we can conclude what? The box is what?
M minus 1 is n plus 1?
N plus 1, right? Some of them. So we should consider two cases. Let me do something. Let me make this part smaller. Then let's make also this part smaller. Okay, so we have two cases. Let's consider that, for example, if we reach n plus 1. If we reach n plus 1 means n plus 1 is less than or equal m, right?
Right.
Is it correct?
No, n plus 1 has to be greater, unless it's equal, but n plus 1 has to be greater than equal.
So only for this case we reach 0, it seems, right? Because look, some of them is n plus 1, and we will check for small cases. So for n plus 1 we reach 0, right?
Right.
Then what happens?
Sorry?
Then what happens in this case? From here,
Isn't that it? It stops.
first j minus 1 would be 0, right? R2, look, second part of each part is first j minus 1 r's, right?
Right.
And do you agree we know this one is at least 0, right?
Yeah.
So only in last part we can have 0, right? In this one.
Oh, okay.
Second last one. So it means that n plus 1 is m, right? So in only mth one it would be 0, right? N plus 1. So m minus 1, which is equal to n. It is 1. And in next box, which is m or n plus 1, it is 0, right?
Right.
Okay, what happens in this case? Let's see, is it okay or not? This R2 is second part, or first j minus 1. But do you agree we know that first j minus 1 of this is not 0? It's j minus 1.
Yeah. First j, yeah.
But why we reached 0 for last part? Let me copy this figure.
But isn't that like the part in M, like the second half of M?
Let's check. It is 1. It is second one. It is mth one, right?
Right.
R2, R1 is first part, right?
Right.
R1 here, it is this one, R1, right?
Okay.
This one is this one is R1 of first part. This one is R1 of second part, right?
Mhm.
This one is what? This one is R2 of first part, right? R2 of first part, we said it is J minus 1, J minus 1 to this. So do you agree R2 of M should be J minus 1 always? Agreed or not?
It for R2 till what?
R2 of last box. R2 of last box means reds of second part of that, right?
All right, it should be J minus.
It should be
1.
J minus 1. But here, what's the problem that we considered 0?
Oh, because weren't you saying? Oh no, I'm not sure. No.
We said if you consider n minus j plus 2, how many reds are there? Some of them we said is n plus 1. So we said j minus 1 reds, right?
Mhm.
Then in next part, I found it. N minus 3, we said j minus 2, right? But do you
Right.
agree when it is second part of something? Look, when it is
Mhm.
first box, first part, this one. Let's consider this one. A square one, circle 2, okay? So, it is what? It is circle, right?
Mhm.
So, it would be which box?
N minus J plus 2.
So, let's check. Box 1 goes to circle 2. So, what box goes to circle n minus j plus 2?
N minus J plus 1.
Exactly. So, if you consider R2 n minus j plus 1 is j minus 1. But if you consider next box is what? N minus j plus 2. For n minus j plus 2, it is j minus 2, right?
Right.
So, it's j minus 2. The previous one is j minus 1, right?
Mhm.
Okay. Now, it is j minus 1, j minus 2. So, this one is j minus 3, right?
Right.
Okay. If it reaches 0, it means what? Some of them is what? Some of them is n, right?
Mhm.
If it reaches 0, it means what? It means that it is n minus 1 because some of them is n. It is 1. If it is n, it is 0. Then we know that m is at least in general n plus 1, right?
Mhm.
So do you agree when this one reaches 0 means m is n plus 1 exactly?
If N reaches 0, so it's going to.
This one is what box? This one is box m minus 1. Do you agree only m minus 1 can be 0, right?
Right. Okay.
So it means that they should be equal. Then next box, which is m box or n plus 1. This box would be what? How many ones are there in second? J minus 1,
J minus
right?
Mhm.
Okay. Now, let's consider our first boxes. You said n minus j. This, okay, so now we want to consider number of reds, okay? But maybe we won't reach 0, right? We have also the case that we cannot reach 0. That's the case that m is strictly greater than that, right?
Right.
Okay, so for this one, let me move this a bit to right to consider also this one. This is n minus j plus 1, right?
Right.
We said it is j minus 1, right? Because in n minus j plus 1, first this j minus 1 here, all of them are red, right? Okay, and now let's check again R1 to make sure they are correct or not. For R1, we said, okay, first box. First box considers what these are. This part is easy because at first we have this number of reds, right? Then step by step it will be decreased by 1, right?
Right.
And always it reaches 0 or not. It's not important. In n minus j plus 1 it would be 1, right? Some of them is n minus j plus 2. After that it's 0. Maybe we reach, maybe not, right?
Okay.
And here, as you can see, until here, all of them constant. Here, from here, all of them would be 0 in first part. And then we can say what here. Let's consider under what case we reach 0, okay? Here. We found this. This is for n plus 1m. So if you reach 0, it means what?
Means J, 2 minus J is less than 1? Or J
Let's
is
consider
greater?
something. Do you agree some of them is n plus 2? So some of them is n plus 2. And it is n plus 1. So do you agree in this case it should be 1 to have n plus 2? Previous one 2. If n
Isn't
plus
the
1
sum
is
n
m.
minus J plus 2?
Can you say it again?
Isn't sum n minus J plus 2? Or
Sorry. N minus j plus 2. So under what case we reach 0?
n plus
If
1 is n
n minus
J
j
plus 2?
plus 2 is less than or equal m, right?
Mm-hmm.
If we reach this box, then it reaches 0. This box, if it is less than or equal m, then we have this, right?
Right.
In this case, n is m minus 1, right? Agreed. In this case, we said n plus 1 is m. So n is m minus 1. Agreed? So we can cancel m. So j is at least 1, right?
Right.
And obviously we know j is at least 1, right? So we reach 0, right?
Right.
And in this case, okay, so we reach 0. Now let's consider number of reds, okay? And then after this, we consider the cases that n plus 1 is strictly greater than m, right?
Right.
So how many reds are there here? Some of them is n. Next one is what?
N minus 1.
Next one is what?
N minus 2.
This one is what?
J.
Yes, this one.
J minus 2, J minus 3, and it keeps going down till 1 and 0, and then J minus 1, so they're all distinct.
Yes, good job. Finding this example is so much hard without considering small examples, right? Okay, now let's consider the case that, let me paste it here. Now let's consider the case that n plus 1 is strictly greater than m, okay? So then what can we say? Here we won't reach 0, right?
Right.
So let me copy this case also. So we consider this for R2. For R2, it is j minus 1, j minus 1, j minus 1, then here, j minus 2, right?
Mm-hmm.
And what happens to R2 when n plus 1 is strictly greater than m?
What happens to?
Instead of these things, we should place what? Here we cannot say it is not n anymore. It would be m minus 1, m minus 2, right?
Uh-huh.
So how many reds do we have here?
Oh. M minus n plus 2j minus 8?
Let's check this. Do you agree? This is increasing by 1, it is increasing. It is decreasing by 1, it is increasing by 1, right? So the sum of them would be constant. Sum of them is what?
Oh, j.
This plus this is j?
Oh, n.
N. So for this one it would be what?
N minus m plus 2?
Exactly. N minus m plus 2. For this one it would be what?
N minus m plus 1?
Okay, and do you agree? We can say always it's correct for also previous case. It is general form of previous one, because if it is equal, it would be 0, right?
Right.
Okay, now what about this part? This part is first round. First round is 0, 0, 0, 0, 0, 0, 0. All of them 0, right?
Mm-hmm.
Okay. Now number of reds would be what? So we didn't need to consider this case, okay? Because it is general form of that, right?
Right.
So number of reds n minus 2, j minus 2, j minus 3 here would be what? Sum of them, right?
Oh.
R1 plus R2. It is what?
N minus m plus 2, n minus m plus 1.
And this one is what? J minus 1, right?
N minus 1.
Now why all of them are different? Number of reds here in this row.
Right.
Why all of them are different? Want hint for proving all these numbers are different, or want to do it on your own?
Could you hint? Because isn't it possible j equals n?
Let's check the numbers. J is from 1 to n, right?
Right.
So it's n minus 1, n minus 2 to j, right?
Mm-hmm.
Then what? J minus 1, j minus 2 decreasing, right?
Right.
To, because it says it is decreasing until n minus m plus 1, right?
Right.
So you're only,
it's
here we said
decreasing
it
from
is
n to e.
decreasing to reach j.
Oh,
Okay,
okay.
n to j.
Oh,
So if, for example, j is equal to n, we have only n, and then n minus 2, n minus 1. Okay?
okay.
We know
Oh.
this part is decreasing from n to j, okay? Then we have a jump, j minus 2 to this, again decreasing, because these numbers are decreasing. Then again we have a special number, j minus 1. So it is important to prove between them we don't have an equal number, right?
Oh, okay.
So n to j, j minus 1 to n minus m plus 1, j minus 2 to n minus m plus 1, this one. J minus 1 strictly is less than minimum of this and greater than maximum of this, right?
Uh-huh.
Okay, so we proved all of them are different, right?
Right.
Okay, so any question about this problem?
No, I think it's okay.
Do you agree this problem didn't have any special idea? We should again work on a small example and try to prove something like this, right?
Right.
Okay, this approach is so much useful. In your next exams, again, you need this approach. And I can say in all exams, we have some problems, more than one problem. So let's try